Right.
So
Yep.
instead of smashing everything, it kind of needs to go in a flow or something like that.
Yep.
Yeah,
Yep.
so
Yep.
we're learning, basically, we're still learning, and hopefully we'll learn from other teams
Mhm.
more than, yeah.
Yep. Great. Nice.
Yeah. Thank you so
Um.
much.
Yep. Thank you. Stay engaged. So yeah, we'll open source the data that the models and data, and I'm sure the best model is to come. Like it's not there yet.
Yeah.
Once
Yeah.
we learn from each other. Um.
Yeah.
Yep. So okay, let's move on to the third team, Bristol.
Hello, can you hear me all right?
Yes.
Thank you. Maybe I'll give a brief intro of myself and our team.
Yep.
Hello, everyone. My name's Jun Wang from the University of Bristol in the United Kingdom. My research is about power electronics, and I've been also working on the characterization and modeling of high-frequency magnetics. For example, we've developed a testbed. We call it triple pulse test for low cost but large signal testing for magnetic components with DC bias. And so it's a pleasure to participate in this competition. Thank you for organizing. So our team is a team of two undergraduate students, Li Zhong and Tom, here in the call, and two postgraduate students. So this whole machine learning technique is actually quite new to all of us. So it has been a good learning curve to climb for everyone. But luckily, we've got some support. One from a academic, my colleague from the mathematics school, Dr. Song Liu, and a industry advisor, Alfonso from Worth Electronic.
I think Alfonso's here, right? Alfonso,
Yeah,
do you want
Alfonso's here as well.
hi as well? Yeah.
Hi,
Yeah.
nice to see you.
Yeah, just wanted to take this chance to say thank you for them to support us. So in terms of the challenge, it has been very interesting, and we've actually tried quite a few things. And we've done like FFT as well. We've tried transformer, tried XGBoost, we tried LSTM, all of that. So eventually we've picked a internal winner to submit for this competition. And the majority of the work is done by the students in our team. So for now, I'll hand over to Li Zhong to give a introduction of the final selected model from us.
No problem. Thanks, Dr. Jun. And let me just.
And we're
Sure.
happy to hear the models that were discarded. Why do you throw them away?
No problem.
It's just slightly less good.
Like, since I'm on iPad, so I'll just go. Can you see my screen?
Yes.
Yep, all good.
Yeah. So basically, just use this short presentation to talk through some points I think that might we do a little bit well on. So the first one is a multi-step transfer learning pipeline. Basically is the graph right here. And rather than just started from all zero or start from nothing, we chose to start from 10 material to train the 5 material A, B, then C, D, and E. Basically, you can see from started, and we train 10 materials to get a pool of materials as a basis, 10 bases, and chose the best material. For example, in this example is material C. So chose the best material from 10 trained material as a basis to train does the fine tuning for the material C. You get my point? Yeah, that's, I think works pretty well. And
I just wanted quickly to add, now we know material C is 3C95, so it's quite close to the model we chose.
Right.
We chose 3C94 for this one.
I like this. So how do you match this? I have a question about this. It's like if your if the two surfaces of the two core law surfaces are linearly spaced, but they look very similar, how do you compare this similarity? How do you select the best fit?
Yeah, that's it. I can tell you like
Yeah.
I find white space.
Mhm.
So for example, 3C90, it has the the arrow distribution of this, and here's the origin. Here's the origin. So we don't care about the mean of
Okay.
the arrow.
I see.
Right.
Okay.
We only care about the standard deviation of the loss, which
Right.
how convergent is this part.
Okay.
Because we, in next stage, which is the stage right here, we will divide the mean. Oh shit. Can you still see?
I can see.
Yep. We will divide basically divide the mean of the arrow to make the arrow become like this. So basically back to the 0.
Okay.
Yeah.
So basically standard deviation is what you care.
Yes, standard deviation to select model. Yeah.
Yeah, I do personally. I think it's open for community discussion. Personally, I think a material similarity checking tool could be very, very useful. But what is the characteristic? Whether we go with the, like you said, standard deviation, or how do we? What is the most important character? Maybe even go back to more of a Stemmer's equation type of method could also have a room here. So yeah, I really like this approach in finding a material that looks most similar to the new material. Yeah.
Yes. Thank you.
Just to add, we also tried another method just to look at the permeability of the material to find the similarity. But I mean, the permeability could range quite a lot. That one couldn't help us to actually pinpoint a particular material.
Right.
Yeah, and this one worked the best in the end.
Right. Basically, we're trying to find a fingerprint of a material. What is that fingerprint? We don't know yet. So this is a good try. A few teams tried this type of method, and they usually tend to get very good results. So, good.
Yep. No problem. So for the second point, basically it's a decoupling of the phase shift. And yeah, so in this, let me just clear this one. Yeah. Rather than insert all the temperature, frequency, and the B waveform into the LSM together, we chose to insert the B waveform just inside of the LSTM. Basically, use the LSTM just for the waveform extractor, waveform feature extractor. So this part. So if we do the transfer learning, the parameters can be remain in most extent. And so we don't want this part to be very sensitive with the phase shift of the B waveform, because the B waveform originally is basically a periodic signal. The phase is not importance in my options and in physically. So I basically make a random shift and flip for the training. Like basically is to make that like this kind, to shift that and do a little bit flipping like this kind. Then another advantage of that is it extends the data set like 256 times of the data set. that also provide a more generalized to the result for the model. Yep. And yes, and for the testing data set, because we random shift and flip it, so for the inference part, basically the forward part, we also try 100 times of the forward, because every time you forward, it will get the different results if you try to apply the random shift and flip, and average them. It will avoid some of the extrema errors. And for the third one is the data imputation for small unbalance. This one is probably we do well on the material D. Yep. So that's probably the reason, because we use a classifier to classify the different waveform to extract the triangular and trapezoidal wave from all, because the trapezoidal and triangular wave is very small. The amount of that is pretty small, but in the test data set, it become very big.
Right.
Yeah, we duplicated the triangular and the trapezoidal waveform and added into the training set to adding the power of the weight of the loss function.
Right.
Yes.
Your team did well on the model D. Like material D, you guys are #1, I remember. Oh.
Yeah. Thanks.
Congratulations.
Yeah, so since I think today we got a little bit more time, so I could move a little bit about the software engineering part. I think that probably could support us to do this much of the testing. So I would move on my pad to the let me see, to my desktop. Let me see. Share my screen.
So you think for material D, the reason why the good result come from is the way the classification is helping a lot?
I think it contribute, but I did this lot of the transfer learning is also the basis.
Okay, so basically your model learned a lot of information from other materials already.
Yes.
But what do you find as most similar to material D? Did you try that or no? No.
I forget. I
Yeah,
can.
no worries. So basically you again for material D, you do a quick evaluation, find which material looks most like material D, and then start from there.
Yes, basically.
Yeah. Good.
Yes, and stop sharing.
I think the efforts we did on decoupling the sensitivity to the phase and flip of the B waveform also contributed to the good results. Since the material D is the waveform challenge, so I think that has helped.
Right. Dixon, there's a question.
Yeah, please.
Go ahead.
Yeah, a small question. Since you guys increased the data so much, how did you guys prevent overfitting, or something like that? Like if it learns too much of the same pattern or something.
Prevent overfitting. I think if it's overfitting, that will perform very bad on the validation data set. So we won't choose that model. Basically, the model is we chose from I test too much. So
also, we didn't duplicate we didn't artificially expand the training set that much. And also the duplicated sets, we still apply the random shift and flip on it. So to the neural network, I think, at least from the waveform point of view, the duplications, they don't look all the same.
All right, thank you for that.
Yeah, so for the flipping side, one comment I may have is this competition, we don't have DC bias. so you can do flipping.
Yeah.
Future, in a more general case, if we start to do DC bias, then flipping is dangerous.
Yes.
Agree.
No.
Thank you.
Yep.
Yes. So, can you see my screen now?
Yep.
For the
Not yet. Yes.
Yeah.
No.
Yeah. So that's basically the training structure of this. Basically, when I start to doing this project, I treat this as a entire project. So I think it's not from this is not related to neural network, but some for the engineering side. So I think is how can I do the iteration to try as much as the different structure of the neural network. So I built this architecture. So basically, so this one is only for the neural network and those for the training and others. And so an interesting point is I training on the Google Colab. So I did some compatible layers to let the training can also be run on both on the desktop and also the Colab. And you can simply, if you want to change the neural network structure, you can just simply just copy that and duplicate that and modify the neural network structure, and you can have a new structure to test. So I think that's probably the reason we can test so much of the neural network structure and the different strategy. Yes, I think, yeah. That probably is all I want to say. Yeah.
Great. I forgot. Did you guys plan to open source this, or I forgot? Maybe you're going to open source through your channel or something like that. I think some of these tools are very useful.
Yeah, we've read to open source.
Yes.
Yeah. Great. Yeah. So I think that's helpful. Good.
Yeah. And
yeah.
Yeah. Please.
Great. Go ahead.
Li Zhong, do you have anything else to say?
Yeah. I'm basically finished.
Okay. Yeah, I was just gonna say at the end we also plan to do a bit of model distilling to shrink the size of the model, but the time was quite tight. It was right before Christmas at that point, so we didn't manage to do that. But I do believe the model size can be shrinked further.
Yeah, I guess save it for the publication. Like in your papers, you can
Okay.
show much better results there.
Yeah.
Yeah. Haran, Shukai, Tom, any comments?
Yeah,
Hey,
not really.
yes.
Yeah.
Yes, William Kirchgessner. I have a question to the recurrent architecture you use. And
Yes.
my question is, have you investigated whether the initial value has some impact on your predictions? The initial
What do you
value
mean
in
the
your
initial value?
LSTM.
Sorry.
Initial value. I guess the question is like, what do you mean by initial value?
Yeah, for the LSTM, you have to define the initial cell state of the LSTM layer. I think there are 2 cell states in the LSTM, and by default it is 0, but you could also set it to some other value. The question is whether you had time to investigate that.
Oh, I haven't so for your question, you mean when inserted to the LSTM, so the first the raw state is 0. Yeah. Yes, we keep the raw state into 0 and feed into the waveform data. Is that what you mean? Sorry.
Yeah, it goes into that direction. So input data is one thing, but those recurrent structures, they also have cell states or stateful in some way, and most of the time or per default it is 0. but you could also play with these values if you apply recurrent neural networks or LSTMs also. But yeah, I
I think
guess it
that
was just 0 then.
proved that. Yeah.
Okay, thank you.
Yeah, have you guys used 0, but looks like Wilhelm is suggesting maybe you can try with others.
Yes.
Yeah,
That's
right. It
improvement.
could be, you could set as initial value maybe something like your best guess what the H value should be.
Yes.
I see. You can basically, the way I understand is that you can assume a permeability, a linear
Yeah.
permeability, and then get initial B from the edge or vice versa or something like that.
Something
Yeah,
like that, yeah.
Yeah.
Right.
Yeah, good, great.
Mm.
Any other comments?
I just wanted to add that Tom from our team also tried a couple of other methods. Tom, would you like to talk a few words about the other methods you've tried?
Yeah. Can you hear me okay?
Yeah, all good.
Yeah. So yeah, I kind of developed a slightly different model. Originally I was going for a transformer approach as opposed to an LSTM. And I was kind of looking at it just like purely from like a sort of maths perspective. So trying to like characterize the B waveform as well as using it with FFT. And then look at sort of things like the standard deviation of that, like the mean of the waveforms, and like lots of like mathematical parameters basically. Yeah, it got okay results. I had to do like a lot of testing with it to sort of see which parameters were like contributing to it, and which were sort of like negatively affecting it. So I used a lot of like tests for that and kind of like whittled it down to like just, I think it was about like 16 input parameters. And I used a relative, I slightly modified the loss function. So turning it from like a mean squared error loss to using like a relative loss. And it ended up getting like quite good results on the pre-evaluation set. So like on some materials, it got like within a few % of the LSTM approach. Yeah, when we tested it against the final batch of data, it was about the 20% range. So I think like to improve it, it'd probably be worth trying to go back to the transformer, because I used XGBoost eventually with it, and to try the data augmenting, because that was sort of like one of the key things that kind of like took our values from like 15-20% error to like less than 10. So yeah, that's sort of a brief summary of it.
Great.
Yeah.
Okay, I think that's all we have. Tom, are you back? Tom Guilot, are you there? I'll try to ask him to unmute. He's also one of the core members of our team, but looks like he's not there. Anyway, that's fine. So I think that's all we have for today. And as you guys know, we'll run this for 3 days. Same time tomorrow. There will be 8 teams tomorrow. So I guess we have to be keep the time. Like 3 teams, we barely make it. So we'll see a bit more information into tomorrow's and the sessions on Friday. So yeah, so that's all we have for today. Thanks all the 3 teams, SAL, Triple Van, and Bristol. And we look forward to seeing you guys tomorrow.
Thank you.
All right, thanks all.
Thank you. Bye.
Bye.
Thank you.
Thanks. Bye.
Bye.
Bye.